Right. In this lecture, we are going to study reasoning with Bayes networks. So, in the previous lecture, we had seen how to create a Bayes network and what is the meaning of a Bayes network. And today, we are going to see how an existing Bayes network can be used to reason about different kinds of events. So, we will continue with our example on the burglar's alarm and try to see how to compute different kinds of probabilities values using the given network. Right. So, just to recall very briefly is that what actually we have in this belief network is that we have conditional independence, in the sense that the probability that a given variable takes a given value given the values of all the other variables which precede it in some ordering is given by the probability given the values of the parents. So, for example, if we look here, then the probability of John calls given alarm and earthquake is the same as probability of John calls given alarm. Right. The non parents of John calls, namely burglary, earthquake, etc., do not affect John calls directly if we are given the value of alarm. Right. If we are given whether the alarm has rung or not. Right. So, this is what is the representation of belief network or Bayes networks attempts to do. What we shall now do is that we will try first with some examples, see how we can compute different kinds of probabilities with this. Then we will study the general algorithm for computing those event probabilities. So, we will start by looking at what is called diagnostic inference from effects to causes. So, what we are interested in finding out is probability of burglary given John calls. So, probability okay, I will use short forms. So, for burglary I will use B and for John calls I will use J and so on. Right. Now, the question is how do we compute this value from the given belief network? The given belief network has only some conditional probability values. So, this is how we are going to do. We will compute P B given J first as probability of J and B. So, I will write that as JB, right, divided by Pj. Right. Now, let us see why we are doing this. Now, if we go back to the belief network, then you will see that according to this belief network, John calls is actually an effect, can be actually an indirect effect of the burglary, because if the burglary takes place, then the alarm may go off and then John calls may happen. But what we are trying to compute here is probability of burglary given John calls. So, we are given that John has called and we are interested in finding out what is the probability that actually a burglary has taken place. Right. So, this is a diagnostic inferencing. So, in order to find out these kinds of probabilities, see in these conditional probability tables we are given probability of John calls given alarm, probability of alarm given burglary and so on, but here we require it the other way around. We want probability of burglary given John calls. So, in the first step that we have done here, as you can see that we have converted it into a form which is suitable for us. So, we have converted this using Bayes rule to P j and B divided by P j. Right. Now, how do we compute P j and B? To compute P j and B, we break it up into PJBA plus A prime, right, where A is alarm. Now, we can always do this based on any variables, but we are doing it on A because we know that J depends on A from the belief network structure. So, now we have to compute PJBA and PJBA dash. So, this we can compute again as P j given A B, right, times P A B, right, and the other one is P j given A dash B times P A dash B, right. Now, P j given A B is the same as P j given A. Why? Because if we look at the belief network structure, then you will see that P j given A and B is the same as P j given A, because A separates B from J, right. So, we will have this simply as P j given A, and then the next term is P A B plus P j given A dash. For the same reason, B will disappear from here, times P A dash B. Now, this I can get from the conditional probability table. P j given A, if you look at the belief network, it is given as 0.9, and P j given A prime is 0.05, right. So, this is 0.9 times P A B plus 0.05 times P A dash B, right. Now, see, what we are doing is essentially we are going from bottom upwards, because that is the way in which it is easier to compute in the belief network, because the conditional probabilities are given from bottom to in terms of the parents, right. Now, we still have to compute P A B and P A dash B. So, let us continue how to compute P A B. So, if to compute P A B, we can compute that as P A B E plus P A B E dash, right. That we are introducing this E because A has two parents, one is B and the other is E, right. So, then again we can rewrite this as yes. P A B yes, you can write it that way also. What we are doing here is we are writing it in this way, because now what we can do is we can just look up this thing as follows. this is going to be probability of A given B E, right, times probability of, and B and E are independent. So, I can similarly this is probability of A given B E dash times probability of B E dash, right. Again what we have here is this value we can get from the belief network. So, if you look at the belief network, probability of A given B and E is 0.95, right, and probability of A given B and E dash is also 0.95, right. So, if we use those values, then we get 0.95 here times PBE. Here B and D are independent. So, that is just PB times PE, right. So, PB times PE will be 0.001 times 0.002 plus this is going to be 0.95 times probability of B, which is 0.001 plus probability of E dash, which is 0.998, and so this comes out to be 0.00095, right. Then similarly we have to compute P A dash B, and if we use a similar calculation exactly similar to this, then we find that to be equal to 0.00005. Now, if we coming back to our original thing, we now have the values of PAB and PA dash B. So, we can write this as 0.9 times PAB was 0.00095 plus 0.05 times 0.00005, and this comes to 0.00086. So, after doing everything here, we have succeeded in computing the value of PJB, right, but we still have to compute the value of PJ in order to get this, right. So, we now have the numerator which is 0.00086 and we have to have the denominator Pj here, right. Now, how do we compute Pj? How can we compute Pj? We want to find out just the probability of John calls. So, Pj, yes, how do we compute this? Right. So, we again will break this up into Pja plus Pja dash, right, and then we go again similarly as Pj is broken up into Pj given A, which we can find from the conditional probability table, times Pa plus Pj given A dash times Pa dash, and then again P j given A we can find from here. Okay, Pa and Pa dash. How do we compute Pa and Pa dash? So, again similarly we just break it up into 4 cases, right. So, we break it up into P A, yes, say right, B E plus P A B E dash, right, plus P A B dash E plus P A B dash E dash, right, and then we can break up each of these as P A given B E times P B E, right, plus P A given B E dash times P B E dash, and so on. So, we get 4 terms like this, and in each of them the first term can be obtained from the Bayes network, because we are given the probability of alarm given B E and B E dash and B dash E and B dash E dash, and the second term, in the second term B and D are independent variables. So, therefore, this will split up into P B and P E and P B dash and P E dash, and we can find out those probabilities again from the belief network, right. So, if we do all this, then finally, we will find out that this is P A is going to come out to be 0.0025, and similarly when we compute P A dash, right, that we can obtain by 1 minus this thing, and then when we substitute the values back here with the values of P J A and P J A dash, then we get the value of P J as 0.052125, right. Now, having and then once we have this value, then we go back to our original thing, and here instead of P J we now use 0.052125, and then this gives us 0.016. Yes.
So can you calculate the probability of
P A given B. Yes. So, it will become P A given B E plus E dash, right? Yes. Okay. So, all this analysis put together gives us this P burglary given John calls is 0.016, right. Now, see what essentially we are doing is, we are in the first step we are converting it into a form where we have the cause rather the effect in terms of the cause, right. So, suppose we have a variable A which influences a variable B, we are trying to recast the computation, so that we compute the probability of the effect given the cause rather than the cause given the effect, right. Now, for example, in some cases where we have causal inferences, where we go from causes to effects, you will see that the computation is usually much easier. So, suppose we want to compute P John calls given burglary and P Mary calls given burglary, right. So, these we shall find in these we have it in the right shape. Only thing is that John calls does not directly depend on burglary, right. It depends on whether the alarm has gone off or not. So, if you look at P J given B, now see we previously we computed P B given J, now we are looking at P J given B. So, this is a causal inference. So, we will rewrite this as P J B divided by P B, right. And then again we proceed just as previously, right. Similarly, for P m given B, we will do the same style. Is it clear? Okay. What about intercausal inferences between causes of a common effect? Suppose we are looking at P B given A. So, we use the same style, P B given A, convert it into P A B divided by P A. So, we are always converting it into the joint probability distributions queries, right, and then using the conditional independence of Bayes networks to filter out certain variables and evaluate the rest. Right. Now, with this background, let us the complete analysis of all these different kinds of events for this particular example is available also in the course web page, right. So, there is a PDF file there which shows the detailed computations of each of these, right. So, if you are interested, you can download that and have a look at it, right. So, these are the 4 kinds of patterns that we have seen: diagnostic, causal, intercausal and mixed, right, where Q is the query and E is the evidence. E is the evidence, E is what is given. See, in the first case, what is given to us is a successor in the belief network of the query. Like for example, here the query could be that probability of burglary given John calls. So, John calls is the evidence and burglary is the query that we want to determine. Then causal is where you where the query is further down in the belief network. So, it is like probability of John calls given burglary, right, and this is like probability of burglary given earthquake, right. Huh?
So P of B given A won't be a intercausal.
P of
B given A will not be a
burglary given alarm.
will not be a intercausal inference.
No, it will just simply be causal. Probability of burglary given alarm. No, that is going to be diagnostic. Diagnostic. Okay. Intercausal is where they are brothers. The query and the evidence are brothers, right? They are siblings in the network. And mixed is where you have evidence at the top and evidence at the bottom, and you are looking at the query in the middle. So, suppose we want to ask what is the probability of the alarm given earthquake and John calls.
Sir, if we can represent 2 in any of this kind of, then those are not dependent on each other. Like here, if we ask means John calls and Mary calls, we can find a relation between these graphs. We cannot find a probability like probability John calls given Mary calls.
Oh yes, we can.
We can prefer
Probability of John calls given Mary calls. No, they are not independent.
So which one will be of
They are not independent, because if one calls, then that is increased probability that the other will also call. You see, if John has called, then he has probably heard the alarm, right. So, therefore, it is it is also increased probability that Mary also calls.
So does this fall under any of the four categories?
Yes. That
Probability that John calls given Mary calls, I think it will come in mixed, right. It will come under mixed. No, it will not come under intercausal. Intercausal is where they are together, they are affecting something which is they have a common successor, but here they have a common predecessor, right.
Suppose Q and A are mutually exclusive,
Mm.
like burglary and earthquake, then probability of burglary given earthquake is same as probability of burglary.
Probability of burglary,
Given earthquake.
yes, burglary and earthquake are independent events. So, probability of burglary given earthquake is the same of probability of burglary. Yes. Right. If you recollect, in the last lecture we had talked about conditional independence, and when in the belief network two events are conditionally independent. It also depends on what evidence you have. Like for example, when we are talking about the car starting example, then when you knew whether the car starts or not, then the events of the radio and the petrol were no longer independent, otherwise they were independent, right. So, mixed here is going to encompass everything else. So, this is a general thing, and this general thing is what we are going to study, right, and these other things are just special cases of them, but the algorithm that we are going to study now is going to encompass all of these, right. So, it is going to work for all four of these cases. So, now we are moving into the algorithm, and it is going to be similar in flavor to the analysis that we did here for this example. Now, we are going to consider belief networks which are polytrees. So, which means that there is at most one undirected path between any two nodes. So, the example that we saw here for the burglar's alarm is also a polytree, because if you take any pair of nodes, then there is at most one undirected path between the two nodes, right. Okay. So, this is the general view that we are going to consider. So, our query variable is x. So, we want to find out the probability of x given a set of evidence E, right. What is evidence E? Evidence E is a set of events whose values are given to us. For example, evidence could be that the alarm could be an evidence, earthquake could be an evidence, right. Mary calls could be an evidence, right. So, evidence is the given values for some of the variables in the belief network. So, it means that we are given the values of some of the variables in the belief network, and we have to compute the probability of x given those values, right. So, we are going to represent the set of evidence variables as E. E will denote the set of evidence variables, right. And if you look at x, then x will have some parents. So, these parents are called u1 through um. Let us say that x has m parents u1 through um, right, and x has n successors numbered y1 through yn. Right. Each of these successors can have some parents, right, some other parents. So, we are going to call the successors of yi as zi1, zi2, zi3, zi4 like that. Okay. Is this fine? And then we have to we use Ex plus and Ex minus to denote the set of evidence that we have preceding x and succeeding x. So, if you look at all the ancestors of x, then out of those the nodes which belong to the evidence, which means whose values are given to us, they are clubbed under the set E x plus, and similarly E x minus is the set of evidence nodes which are among the successors or descendants of x, may not be immediate children, but descendants of x. Is this clear? Yes. Right. So, here is what I said just now. U1 through um are parents of node x, y1 through yn are children of x, x is the query variable, E is the set of evidence variables, the aim is to compute p x given E, right. E x plus is called the causal support of x, this is the set of evidence variables above x that are connected to x through its parents, right. E x minus is the evidential support for x, the evidence variables below x that are connected to x through its children, right. In addition, we have two other things, just try to remember this also. What is ui? Parent of x. So, E ui and this is ui except x, this operator in set theoretic terms means except. So, ui except x refers to all the evidence connected to node ui except via the path from x, right. So, it means that ui is a parent of x. So, whatever evidence is there in the ancestors of ui comes under ui except x. Not clear? Okay. Let us go back to this picture, right. So, here is ui, right. Now, ui also has some parents and some ancestors, right. The set of evidence nodes that are there in the ancestors of ui is called ui except x, right. Not only just the ancestors, but also the successors which are not through x, right. So, it is all the evidence that is connected to ui except those that are through x, right. So, if I disconnect, if I remove this edge that connects ui to x, if I remove this edge and then look at the set of evidence nodes that are connected to ui, then that is ui except x, right. Similarly, EYI except x plus refers to all evidence connected to node yi through its parents except x, it should be except x, right. So, if you look at yi, then there is evidence nodes in the ancestors of yi except those through x. So, that comes under EYI except x plus. Is it clear? It will become clearer when we actually go down into the analysis. So, now let us start with the computation. Okay, we are in for some quite detailed analysis now. Now, observe carefully. Okay. Let me do one thing. Let me take down this picture here. So, let us recap this picture once again. So, we have x here, we have u1 through um, each of these are parents of x, right. Okay. And then towards the bottom we have the children of x, so y1 through yn, and each of these children in turn can have their own parents. So, z1 1 through say z1 k, right. Each of them can have their own parents and children, and similarly our y1 can also have other children, right. Similarly, each of these nodes right. So, this is the general scenario under which we are analyzing the probability of x given the evidence. So, evidence nodes are, some of the evidence nodes are in the top above x, which are denoted as Ex plus, and there are some evidence nodes below x which are denoted by Ex minus, right. Right. Now, let us go into the analysis. We are interested in computing P x given E. So, we can write E in as the conjunction of the two sets Ex plus and Ex minus, because that is the set of evidence nodes that we have, right. This is just rewriting E as Ex plus and Ex minus. Then we can break it up using Bayes rule as P Ex minus given x Ex plus and Px given Ex plus, and then the denominator is P Ex minus given Ex plus, right. Now, what we are going to do is, okay, we are, since x deseparates Ex plus from Ex minus, recall that the kind of networks that we are looking at, in that there is only one path between every pair of nodes, right. So, any path which is from Ex minus to Ex plus has to necessarily go through x, right. So, therefore, x deseparates Ex plus from Ex minus, and we can use conditional independence to simplify this first term to simply P Ex minus given x, right. Okay. And the second term is Px given Ex plus, right. And the denominator, see, this denominator is just the probability of the evidence Ex minus given the evidence Ex plus. So, we treat the denominator as a constant and just we will name it as alpha, right. And we know how to compute this for a given set of evidence nodes, right. We are going to come back to this later. Okay. Now, we have two main terms to compute, P Ex minus given x and Px given Ex plus. Now, see, what we have effectively done is we have reduced both of these terms to the form where we have the effect here and the cause here, right, because Ex minus is all the evidence towards the bottom, the set of events towards the bottom of the network, and obviously they are causally affected by x, right. So, both of these are like causal terms, right. We have reduced it into that form. Now, we will compute firstly the first term Px given Ex plus, right. Let u be the vector of parents u1 through um, and let small u be an assignment of values to them, right. So, we are going to break up Px given Ex plus into the sum of probability of x given u Ex plus times probability of u given Ex plus. Now, recall that we had done this previously when we were looking at the probability of John Call's given burglary, when we were looking at probability of John Call's given burglary, that was exactly what we had done. We had broken it up. Let me go back there. Here. No, not this one. Yeah, when we actually started off here. When we wanted to compute PJB, we actually broke it up into PJBA plus PJBA dash in terms of the parents. So, this is exactly what we are doing out here. Here, when we compute this in terms of the parents, so what we are doing is we are inserting all possible combinations of the parent values. So, suppose I have parent U1, U2, U3. So, this is getting broken down into U1, U2, U3, U1 bar, U2, U3, U1, U2 bar, U3 and so on, right, for each of those cases, and then we have the probability of that case given Ex plus, right. Now, see, if your belief network is such that in a given node you have too many predecessors or too many parents, then this term is going to become pretty long, right. So, the analysis is going to become quite complex when you have belief networks which has nodes having many parents. So, that is why it is very important to be able to contain the size of the belief network by proper ordering of the variables. Right, let us continue with this. So, this is what we have. Now, U or the parents of X deseparates X from the remaining Ex plus, right, because if we look at the network here, all the evidence that we have on the other side of this is being deseparated from X by the U, right. And moreover, what happens is that if you look at all the evidence that is around Ui and around Uj, they are also being deseparated by X, right. So, if you look at U2, see, there cannot be any common nodes between, there cannot be any other path from U1 to U2 except the one which is through X, because of the structure of the network that we have assumed. So, therefore, because of this deseparation by X, the evidence around U1 and the evidence around U2 are deseparated, and therefore, the probability of each of these Ui's given the evidence are all independent, right. So, using that, what we are doing here is we simplify the first term here P x U E x plus as P x given U. This we can do because U is deseparating E x plus from X, right, and then the second term can be simplified because this U, what is this U? This is actually a vector. So, it is U1, U2 dash, U3 or U2 dash, U1, U3 dash. Okay. So, it is that vector given Ex plus. Now, if you look at that vector, then each of those individual items U1, U2 dash, U3 etc. are independent given Ex plus. Why? Because they are deseparated by X, right. So, I can split them up into the individual Ui's given Ex plus, right, and the product, because they are independent. So, it is going to split up into the product of their individual probabilities, right. We observed this kind of thing when we looked at probability of alarm given when we looked at probability of alarm given, when we looked at the probability of burglary and earthquake, and we split it up into probability of burglary and probability of earthquake, right. So, having split up this thing, then we look at the last term, and it can be simplified by partitioning this evidence into u1 except x through except x, right, and noting that ui except x deseparates ui from all the other evidence in ex plus. Now, what we are essentially saying here is that, see, there can be some evidence nodes around u1 and there can be some evidence nodes around E2 and some evidence nodes around EM, but these are all independent, right. These are independent of each other because they are being deseparated to x, right. So, we can actually rewrite these Ex plus as each evidence around each ui. So, that the evidence around ui is given by E ui except x, and that is what we can break up the individual probability terms into. So, if we look at this again, then this is going to, this second term is going to be rewritten like this, right. Now, this term p x given u is a lookup in the conditional probability table of x, and this is a recursively smaller subproblem. Right. Okay. So, recursively now we will compute p u y given u y except x, right. So, the algorithm so far will continue up to this step, use the conditional probability here, and then use recursively invoke the algorithm to compute this, right. Okay. Now, all through this thing what we have essentially done is we have finished the computation of this first term here. The first term p e x minus given x, sorry, this term we have computed p x given E x plus, right. This term's computation is done, we have an algorithm for doing it. Computing this term is a little more complex. So, we will leave it for the next lecture, where we will see how we can compute that, and that will complete the algorithm for inferencing using Bayes networks. Thank you.
(1951). A young nation aspiring to find ways to fulfill a dream lays the foundation of an institution that will give aspiring technocrats the license to fly high. The first Indian Institute of Technology is born at Kharagpur. Founded on the basis of the recommendations of the N.R. Sarkar Committee that was set up in 1945 to consider the development of higher technical institutions in India, the institute was first established in 5 Esplanade East, Kolkata, before it moved to Kharagpur in 1951. With Sir Gyan Chandra Ghosh as the first director and Dr. B.C. Roy as one of its founding guardians, the institute established itself as the symbol of a young, dynamic and resurgent nation. As top students rubbed shoulders with the most celebrated of professors and scholars, visions took shape. And IIT Kharagpur continued to play the pioneering role that was envisaged for it, enabling India to become a knowledge powerhouse that it is today. At every stage of its evolution, IIT Kharagpur remained ahead of its times. It provided the best of facilities for the budding technologists, helping them shape their own as well as the nation's future. Indeed, today IIT Kharagpur has blossomed into a time-tested, venerable institute of learning, with the rich experience of converting individuals into brilliant professionals through 50 glorious years. As you cross the campus gate, you feel the distinct nip that is IIT Kharagpur. The spirit of objective inquiry and lateral thinking hangs heavy in the air. The modern township-like campus of IIT Kharagpur, set in sylvan surroundings, is self-sufficient in all respects. From modern banks to the good old post office, from vast playgrounds and well-equipped gyms to modern auditoria and open-air theaters, and from the quiet fiber-optic linked residential quarters for the faculty to the web-enabled hostel rooms for the students. At IIT Kharagpur, lush green bowers of tranquility coexist with smart cards and ATMs. Spread over 690 hectares of sprawling cyber habitat, 120 kilometers from Kolkata, IIT Kharagpur is one of the largest network campuses in Asia. Just the academic complexes itself spreads over a built-up area of about 2 million square feet, of which 150,000 square feet is the new complex that commemorates the Golden Jubilee celebrations. And that's not all. It is the only IIT to have conquered territory beyond its own through cutting-edge courses offered in its extension campuses at Kolkata and Bhubaneswar. IIT Kharagpur is not just about its large campus, but its diverse range of activities. It offers the widest spectrum of disciplines, ranging from aerospace, biotechnology, cryogenics, to architecture, mining and agricultural engineering, supported by strong faculties of sciences, humanities and management. There are more than 30 departments and centers that offer the largest number of undergraduate and postgraduate courses amongst the IITs. The courses are ever evolving and show the way for other sister institutions. The richness in its diverse activities is showcased by the technological support the institution provides in areas like architecture, agriculture, post-harvest technology and medical sciences. The institute has revolutionized and popularized rice milling technology. The other major contributions of IIT Kharagpur have been in the critical fields of defense, railways, space research, power systems and petrochemicals. All these activities directly empower the human requirements of the nation. Advanced facilities at the Institute make it possible to undertake cutting-edge research and service-sponsored research projects. The array of equipment ranges from aerodynamic testing laboratories to intelligent machining centers, atomic spectrometers, to VLSI design labs, molecular beam epitaxy, to anechoic chamber, fast protein liquid chromatographs, to liquid nitrogen plants. The cutting-edge technologies are at par with the best research facilities across the globe. In fact, the volume of research and development activities at the Institute is incredible. In terms of the number of patents it owns, the volume of industrial consultancy it provides, and the revenue that it earns from all these make IIT Kharagpur a class apart and strengthens its position as the true pioneer in technological education in India. The Institute Library deserves a special mention. Indeed, in this golden jubilee year, as the celebration continues, Pandit Nehru would surely have been a proud man today. For him, IIT Kharagpur was always more than just an institute of technology. In his own immortal words, it is indeed